All right, and welcome to the lesson 5.1 notes here. We're actually starting a new chapter, chapter 5. Um, it's a chapter that focuses on, as the heading says, congruent triangles. So we got to define what does that mean for triangles to be congruent. It's really broken into two parts. Really, this first lesson, 5.1, focuses on this part, this classifying triangles by sides and angles, looks at some properties of triangles specifically, compared to some other polygons. And then the second part of the chapter, really from lesson 5.2 on, focuses on this idea of proving that triangles are congruent. Okay, we'll do a little bit of this kind of mixed in with both the coordinate geometry. We'll actually look at a little bit of that today as well. But that's kind of a chapter overview. Today specifically, like I said, no proofs going on in this lesson. This is really um, going over some of the properties of just triangles as a polygon, naming them, and then how do we classify by its sides and angles. So let's jump into it. Today specifically 5.1, angles of triangles. Let's do it. All right, here we go. So definition, I'm not going to pretend like we don't know what a triangle is. I know that's something you learned a long time ago. A triangle is a polygon, and we've defined it even in some of our other stuff. It's a polygon, a closed figure, closed planar figure. We've got three sides. I think the biggest thing here, naming triangles, we're going to use this little symbol, just a generic, just triangle, and then you name it. It doesn't matter how you name it. It doesn't have to go alphabetical. ABC it's saying here, but I could call this also triangle, CBA, just for a different look or whatever. See, as long as you're going in order, and there's not really a way to go out of order with 3 points here, I could go CAB. So I guess, like I said, the biggest takeaway here is this symbol. We still say the word triangle, CBA, and it doesn't matter what the picture looks like. If I had a long, tall, skinny triangle like this, I would still call that just the same symbols, triangle CBA or ABC, whatever I want to call it. Okay, so that's the first part. Using this symbol, triangle, ABC. That's that. All right. Next thing for our notes would be a section of classifying triangles by sides. There's 3 different ways to classify a triangle by its sides, and it's basically what are the lengths of the sides of the triangle. So if I look, I know some of these words you've heard before. I think the one that's probably a little bit new for us would be scalene. So let's maybe work reverse order here. Equilateral triangle, equa means equal or same. Equilateral triangle means all 3 sides are the same. There's different ways we'll know this information. So either if I know side lengths, if I was told this was 10, and this side was 10, units, inches, whatever, we could definitively say, we could prove, kind of without doing a proof, but we could say that, hey, that's an equilateral triangle. All 3 sides are 10 inches long. I could also get more of the geometry kind of markings here where I say, hey, tick marks, and it doesn't have to be 3. It just could be tick, tick, tick. And as long as I see like, hey, all 3 sides are marked as the same, as congruent, then we could call it an equilateral triangle. So there's still this element of like prove something or show for sure that it's one of these 3. Isosceles, we're taking one away. So we know for a fact that 2 of the 3 triangles, or I'm sorry, two of the 3 triangles sides are congruent. Do we know this one here? Could it be the same as these 2? Sure. If it was, we would call it equilateral. So usually you would just see this as 2 sides marked with tick marks. Usually the third side is unmarked. Could it just be marked as different? Sure. If it showed something like this, 2 tick marks, and 1, that's like indefinitely saying like, hey, this side is different than those 2, so it has to be isosceles. The third one is basically taking one more away. It's kind of your quote unquote normal or just typical triangle. I would say these are very specific cases, equilateral versus isosceles. So scalene, really for us to show it with markings, we do have to kind of show that all 3 sides are different length. So our way of doing that would be to use different tick marks for each side. So I can see that this side is different than this side, which is different than this side. Okay, so scalene means all sides are different lengths. So those are the 3 ways that we'll look at, that I'll ask you to classify a triangle by its sides. I could also ask you, and I will ask you, to classify a triangle by its angles. So a different heading, different section. We're not taking a ton of notes here. It's more just kind of pictures. So classifying a triangle by its angles, there's actually 4 different ways we could look at it, and let's just do them all at once. Basically, our 3 classifications of angles: acute, obtuse, and right, and then maybe a more specific equiangular triangle. Now you can see these are all unmarked. This is harder for us to kind of show. We really have to know angle measures for most of these. So obtuse, I mean, although this looks like an obtuse angle, I mean, it definitely looks like it. We just got done saying like, hey, we kind of need to know for sure. Like, how do I know that that's obtuse? So what we're really gonna have to be presented with is numbers. So if all of a sudden this said, hey, that angle right there is 119 degrees. Oh, okay, then I could definitely confirm like, yep, this has got to be an obtuse triangle because it's got an obtuse angle in it. And the same thing kind of goes for right. Right is a little bit easier for us to see because we have a symbol for a right angle. We can just say, hey, that's a right, and that's all I need to see. I see one right angle symbol, done. It doesn't matter what these are. Same thing with this one. I don't need to know anything about these other 2. I just need to know if this one's obtuse, that's got to be obtuse. Acute is a little bit more specific. We would have to kind of know all 3 of these that are acute angles, or basically that none of them are obtuse. Right? If all I know is this is 30 degrees, yeah, that's good. But what if this is 95 down here? So it's one of those ones that, let's just call this, well, let's make it bigger than that. 75 and what do we got? Another 75. Okay, so 75, 75, and 30. Okay, acute, 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 sure. They're all acute angles. They're all less than 90, so definitely an acute triangle. Equiangular's another one that's maybe a little bit easier to mark. I can just show that this angle, and this angle using our arcs, our congruent arcs markings. That's showing that this angle, and this angle are all congruent. Equiangular means all the angles are the same measure. So there's some different stuff going on there. Here's kind of the big ticket question that goes with this. As far as what I'm going to ask you to do, I say either, graph a triangle. So here's some of that coordinate plane stuff as well, that I say, here's a triangle, or graph a triangle, plot these points, here's the vertices. And then there's really 2 questions. And there's more work to it than I think maybe it looks like. Okay, so it says classify triangle RST. So here's triangle RST by its sides. So I've got 3 options, right? It could either be scalene, isosceles, or equilateral. So I can look at it and guess, you know what, this is not equilateral. It's probably scalene. These all look different, but we just got done, again, talking about like, hey, I need to verify or confirm this. So how do I, in a coordinate plane, show or figure out that these side lengths are either, yes, all the same, one is different than the other 2, or maybe all 3 are different? We're going to have to use, oh no, this old friend here, the distance formula, the big one with the square root. Now, again, we don't have to memorize it. We just got to know how to use it and when to use it. We use it a lot in previous chapters. We were finding lengths of sides and proving things congruent. We did perimeters of figures, which is essentially kind of what we're going to do here. So I'll fill it in here. X2 minus X1 squared plus Y2 minus Y1 squared. That's all underneath. I'm trying to squeeze it in here. That's all underneath that big old square root. Okay. So for us, let's do it. Now, if just as a side note, now this one kind of is a mean one because all 3 sides there's no vertical or horizontal sides. But let's say you ended up with a triangle that looked like this. I would say, hey, you know what? One of my sides, it has a length of 1. One of the side lengths has a length of 2. So that's kind of a nice, a nicer triangle. We would just have to figure out what this one is. But in a case like that we're looking at here with our example, yeah, we're going to have to go through the work and figure out what all 3 side lengths are. So let's do it. Let's just pick, we'll start with this RS. So the length of RS. So I'm starting with this one right here. So this is the work I want to see. You can't just say scalene and be done. Say, hey, sweet, that was easy. Like I want to see, all right, how actually long is this RS? So let's do it. 2, so I'm going to go, I almost screwed up there. X2 minus X1, so 5 minus negative 3. 5 minus negative 3 squared plus, let's see, y2 minus y1, 2 minus 3. And you can definitely start to kind of shortcut it a little bit here. I mean, 5 plus 3 is 8. 8 squared is 64. I'm okay with that. Let's see. Plus 2 minus 3 is negative 1. Negative 1 squared is 1. Okay, so this is equal to the square root of 65, and I'm actually okay leaving it like that. I know a lot of us like to actually do the square root of 65, so I got to grab my calculator here and go 65 square root. It's about 8.1. But really, this is only, 8.1. This is the only number I need to see, because basically if I get another square root of 65 down the road from one of these other side lengths, I'd say, hey, you know what? It's isosceles that two of these three are the same. If I don't, if they're all different, I'm going to say scalene. So there we go. Like I said, I think having a step where you just initially lay it out and then doing some of the simplify here in 2.5 steps, I think you'd be okay. I think there's maybe one like this on the homework assignment. So let's do this one right here, ST. So my next side that I'm looking for the length of is ST. So I'm going to get my big old square root going on here. Let's see. X2 minus X1, so 5 minus 3 squared. 5 minus 3 squared plus, let's see what else we got. 2 minus negative 1. 2 minus negative 1 squared. And here's where we can do a little bit. Let's see. 5 minus 3 is 2. 2 squared is 4. And then 2 plus 1 is 3. 3 squared is 9. So this is equal to the square root of 13. I like this because then I don't even need a calculator. I can already tell you that the square root of 65 is different than the square root of 16. So I already know it's not equilateral. If you want to see that as a decimal, let's see here. 13 square root, about 3.6. Okay, one more to go. All right, which one haven't we done? This, again, it looks longer. Maybe it's the same as this one. I don't know. RT. So the length of RT, let's see here. Make sure you're using those coordinates. So I'm using RT. So let's see. X2 minus X1. So 3. We'll put the square root in afterwards. 3 minus negative 3 squared plus, let's see here. 3 minus negative 1. 3 minus negative 1. Let's see. It's going underneath that big old square root. Let's see. 3 really plus 3. 6. 6 squared is 36. And then 3 plus 1 is 4. 4 squared is 16. Let's see. That's equal to 52. Are we saying underneath there? Sure. 46, 52. The square root of 52 as far as my 3 side lengths. So I can see them all right here. Here's one. Square root of 65 was the length of one of my sides. The square root of 13 was one of my other sides. And the square root of 52 was equal to the third side. Why not just finish it? Whatever. 52 is square root of 52 is about 7.2. So I can now definitively, now that I've gone through a little bit of work, yeah, it's a little bit of work, but I can definitively say, like, hey, these are all different. This is scalene. So let's actually make a conclusion here and say, hey, this triangle is scalene. I've got the work to verify it, scalene, yep, all different. All right, we've classified by its sides. Done. The last part, the only one with angles that we can actually do is determine if it's a right triangle. So I'm actually asking you to recall a little bit from what we had done in the previous lesson, actually, 3.45. How do we know if something's a right angle? Like, how would I confirm whether or not this is a right angle, or this is a right angle, or this is the right angle? This is the one that looks like it might be a right angle. What do I have to look at? I have to look at slopes of the lines, because if lines are perpendicular, if they form a right angle, right, what would have to be true about the slopes of the lines? They would have to be opposite reciprocals. Okay, so I'm going to kind of separate this here. I don't think it's a ton of work, because if I have the graph, I can actually just count my rise and my run. So let's do it like this. I'm going to try to section off this distance formula here. Do I have enough room to squeeze it here? I think so. The slope of of segment RS, let's just do it like this. The slope of segment RS is equal to, let's see, it's negative. It's falling from left to right. So I'm going down 1. Let's go back to that same color. Down 1. And then over 1, 2, 3, 4, 5, 6, 7, 8. Down 1 over 8. Sure, is what it is. Let's go with the slope of segment. Let's see, which one do we do next? ST of segment ST. Let's see, that's equal to, it's positive. So now we're going up 1, 2, 3 over 2. So up 3, positive 3 over 2. And then let's do the slope of, let's see, what's this one? RT we call it. R segment RT. So the slope of this line is down. Let's see, 1, 2, 3, 4. Down 4 over 1, 2, 3, 4, 5, 6. Down 4 over 6. So as I look at them right now, I say, no, none of these are opposite reciprocals. But hold on a second. Just be careful with this one right here. I'm glad this came up like this. If I don't reduce this, I'm never going to catch this. What is negative 4, 6 reduced to? Negative 2 thirds. And now all of a sudden I start to compare and say, yeah, actually, you know what? 3 over 2, the opposite reciprocal of that is, flip it over, 2 thirds, and then change the sign, negative 2 thirds. These two right here are if I just want to use some abbreviations, are opposite reciprocals. So absolutely, these two lines have to be perpendicular, forming a right angle, which means that, yes, this is a right triangle. So there we go. Like that's, like I said, that's kind of a big ticket question for this section, using some of the coordinate plane skills that we learned in earlier, really 2 different chapters, where we learned distance formula, and then the previous chapter, which we talked about slopes of perpendicular lines. So a little bit of that going on. We can't confirm one. If it wasn't a right triangle, we don't have enough information to say, oh, it's obtuse, it's acute. So it's kind of a yes or no question, but again, there's some evidence, some work that goes with it. I'd want to see all 3 of your slopes. Okay. All right. Little bit more vocab here. So when we start talking about a triangle, we have 2 different types of angles. So I'm just going to highlight this triangle. Let's see if I can do it without going too crazy. Triangle ABC. Triangle A, B, C. So here's my original triangle. Triangle A, B, C. We have 3 what's called interior angles. And I guess they're hopefully what you would think on the inside of the triangle, right? The original angles of the triangle. So let's just number them. Triangle angle 1, angle 2, and angle 3. Those would be my interior angles. Okay, angle 1, angle 2, and angle 3. Exterior is a little bit tougher. Sometimes people struggle with. It's just they're not a part of the original triangle. So we got, what is it? What are they then? Because it looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9 different potential exterior angles, but I'm going to tell you there's only actually 3 total. So when we extend the sides, and you can kind of see that's been done, all the sides have been extended, you create a bunch of these angles. The ones that form a linear pair with the interior are what's known as the exterior angle. So if I extend really just one of the sides here at each vertex, this angle right here, let's call it angle 4, because 1 and 4 are forming, remember, a linear pair. Measures 180 degrees, is supplementary, are adjacent. Angles 1 and 4, so 4 would be the exterior angle. And you say, wait a minute, hold on, Mr. Kroll. Couldn't you, well, I don't want to take everything away here. Couldn't I also extend this side? And you say, absolutely, sure, 100%. We would just call this angle 4. The point is you would never do them both at the same time and say, like, oh, hey, now you've got angles 4 and 5 are both exterior. They're not both forming linear pairs. I guess they are, but we only have one at each. Each interior has one exterior angle. Okay, it's kind of a long roundabout way to say that, I guess. But However you extend the side, there's one at each vertex. So we would have an angle. Let's see. Let's extend this one here. We can call this exterior angle 5, and then we could extend this one here and call it exterior angle 6. All right. So I guess the big takeaway is if you've got 3 interior angles, you're going to have 3 exterior angles, and that's that. Okay. All right. So that's what is an interior, what is an exterior angle. Next thing here is we start to talk about some more properties. You may have seen this before. This isn't some it's as good as I can do virtually here with, it's constructed like these sides are straight edges and they're not like curved. I didn't hand draw this or anything like that. But if I've got a triangle, and I cut it out of paper and I used a ruler and I brought it up in front of the class, picture me holding this up in front of you and say, you know what, I'm going to tear off this corner. All right. I'm going to tear off this corner here, just again, seemingly random, just tearing off corners of a triangle. And I take the third one and say, you know what, I've got a perfect spot for that. I do have to flip it here a little bit, but it does fit if I can do this. Oh, it's working out so well that all 3 of those angles, and this isn't, like I said, this isn't some magic triangle, although it looks pretty cool, I think. What do I know? I can't tell you exactly what these angle measures are. Is this 60? Is this 7? I don't know that, but I know that when all 3 get put together, they have to add up to 180 degrees. I've got a straight angle going on right here. So that's probably something that I think either you've seen a demonstration like that, or maybe we even just knew. So the first thing we should add to our notes is called the triangle sum theorem, that the sum that says the sum of the measures of the interior angles. So the measure of angle A plus the measure of angle B plus the measure of angle C equals 180 degrees. That's true for every triangle, whether it's acute, obtuse, scalene, take your pick of triangle. That's going to be true for every single triangle. Okay, so we add that to our notes. The one that's, again, I think that's a little less intuitive, that we probably didn't know before this class, that one, the interior one you may have known, is the exterior angle theorem. It says this, that an exterior angle measure is equal to the sum of the 2 non-adjacent interior angles. Okay, so that's a little bit, what, interior, exterior, non-adjacent. There's a lot of vocab going on there. But basically, this angle measure right here, whatever this is equal to, let's use different numbers here, 2 and 3. Whatever these angle measures are, the measure of angle 2 plus the measure of angle 3, when I add these 2 together, it's equal to that exterior angle, which is kind of weird and kind of, what? Like, is that really true? And it is. We don't have to know this. A lot of times we're not going to know what this one is right here, but we can use these 2 to help us find this one, or vice versa. I could use this one to maybe help me find one of these 2. So that's definitely worth adding, the exterior angle theorem. An exterior angle measure is equal to the sum of the triangle's 2 non-adjacent interior angles. Let's look at an example and maybe involves that. So here's one that I've seen, I've seen people take 15 minutes to try to do a problem like this on a quiz or a test. And if you know the setup, it's actually it's a shorter one. It's an algebraic setup, but it's one that if you get stuck, people try to figure out what this one is, because let's throw another variable in here. Let's call this y. What do I know? Like, people want to lean on the interior. This 73 plus this x plus this y have to add up to 180. 100%, absolutely. I guarantee you, like, yes, that's true. But there's too many unknowns. There's an x, there's a y. So I've seen people do stuff like, oh, let's call this x right here. Now all of a sudden you're assuming that these 2 are the same, which we don't know that. So if I know that exterior angle theorem from the previous slide that says, hey, you know what? This angle right here, this is on the outside of the triangle. It's an exterior angle. Its measure is equal to the sum of the non-adjacent, so not this one, but these other 2 angles, the non-adjacent ones over here and over here, added together. There's my algebraic setup. So if I say, here's how we would solve this: x plus 73, or 73 plus x, these 2 right here, when I add those together, have to be equal to this exterior angle right here, 3x minus 9. Again, a little less intuitive as far as, what, is that right? But yeah, so now I go to solve. Let's see, let's subtract an x from both sides. So 73 equals 2x minus 9, and then we'll add 9 to both sides. So that gives us 82 over here. And then divide both sides by 2 to get x equals 41. So there's different things I could do. Like what now I know, like, hey, this is 41 degrees, which is great. Awesome, fine. It wasn't asking for that because it said use a diagram at right to find the measure of angle DCB. So DCB, it was actually asking us for what is the measure of this exterior angle. So I need to make sure that, like we haven't done this for a while, but I get this 41 plugged all the way back in here. So I'm grabbing my calculator. I'm going 3 times 41. Whoops, that's a 41 minus 9. Let's see, 3 times 41 minus 9. I'm getting 114. So the measure of angle DCB equals, I got 114 degrees. All right. So I just kind of happened to pick one. Are there ones that we will use the interior angle? Sure. You know, if it was asking for, let's just say we didn't know any of this. We knew this was 41, and it was asking for the measure of angle Z right here. Well, 73 plus 41 plus Z has to equal 180. There's different things that we're going to do, and I'm going to ask you to do with the interior angles, but I just kind of picked one that I think is maybe a little bit tougher. Going back and forth with this next slide here. Sometimes in some years we skip it. I guess I'll just mention it here. So the first part is it's called what is a corollary. It's basically a corollary to a theorem is a statement that can be proved pretty easily using the theorem. So we end up with this corollary to the triangle sum theorem. Remember, the triangle sum theorem said they all have to add up to 180. The measure of angle A plus the measure of angle B plus the measure of angle C equals 180. That's what the triangle sum theorem just said 2 slides ago. So in a right triangle, basically this corollary says that, okay, you know what? That same theorem in a right triangle, one of the angles is 90, right? So say, okay, sure. Let's just say, basically what we're doing is replacing the C with 90 degrees, right? Because C's a right angle. And then what do? We subtract the 90 from both sides and just say, hey, the measure of angle A plus the measure of angle B equals 90. And that's exactly what we end up with right here. So in a right triangle, basically kind of the long story short, the big takeaway is in a right triangle, which we would know that one of the angle measures is 90 degrees. The other two, without knowing anything else, just saying, hey, this A plus B has to add up to 90. Right, because I already got a 90 of accounted for right here. In the end, if you're saying, I don't really know, I don't really follow you here, Mr. Crow, you can always just go A plus B plus 90 equals 180, like we started right here, and you subtract 90, and you're right back where we started here. So don't get hung up on that one if you don't quite follow that. I just wanted to introduce this idea of a corollary, because there will be some other ones that come up in future lessons, but this particular one I don't think is overly deep. Last one, maybe an application of it right here, I think. So we've got, let's read through it together. Face of a wheelchair ramp shown below. Forms a right triangle. So that's kind of a key piece. It's not marked in the figure, but let's mark this as a right triangle. It told us that forms a right triangle. The measure of one acute angle is 8 times the measure of the other. Find the measure of each acute angle. So it's another algebra one. It's another algebraic setup. We've got these interior angles, 3 on this kind of this shaded triangle right here. I know 90 of them are accounted for right here. So these other 2 angles, this angle right here, which we're trying to figure out, and this angle right here, which we're trying to figure out, those measures, they have to add up to 90, right? Well, we've got this other piece of information that's going to help us set this up. So basically how we would get things going here is just, I'm going to call, these are both unknown, right? So if this is angle X, or if this measure is X degrees, I have no clue what it is. But I also know that this other one up here is 8 times larger than this one. Well, if this is X, this has to be 8X degrees, right? So then there's different ways I could set this up from here. Let's see if we can scroll a little bit to get some workspace. I could go, like I said before, I could go 90 plus X plus 8X equals 180 because they're interior angles. Or if I wanted to maybe apply that corollary and just say, you know what, these all add up to 9. These all add up to 180. I've got 90 right here, so can I just work with the 8x plus x and say that that's equal to 90? And I sure could. So because the only thing that changed really is I subtracted a 90 from both sides. So that's what I meant, that however you see it, we're going to be able to get to the same spot. So whoops, the only thing left to do is to finish it here and just say, all right, well, what is x? Take your pick. Let's solve this one because it's shorter. 8x plus 1x is 9x equals 90. We'll divide both sides by 9 to get x equals 10. I do have one of the angle measures, so it didn't specifically say this would end up being a 10-degree angle, and this one up here would end up being an 80-degree angle. So I could quick check. 80 plus 10 is 90. 90 plus 90 is 180. Sure, I found the measure of each acute angle. One was 10 degrees, one was 80 degrees. So there you have it. I think that's it. I'm checking my slides here, but not a terrible lesson as far as length, concept. I think there's a lot of stuff there that you may have heard. Pay attention, give good effort on the exterior angle stuff. I know that that's probably a new concept for a lot of us. And then get that practice using that distance formula, looking at slopes here, coming off some of the other chapters. So I think we hit our goals for the day. 5.1, we talked about the different ways to classify triangles by sides and angles, and then using some algebra mainly to find the measures of interiors and exterior angles of triangles. So I think both of those can be checked off and we can call it a day. So there you have it. There's lesson 5.1, angles of triangles notes. I will see you in future lessons.